Hello. We are continuing here with the topic of exponential functions, but in this video, we are going to focus on the natural exponential function. All right, so 4.2, the natural exponential function. Okay, so in the previous section, we looked at exponential functions. So we looked at something like 2 to the x, or 3 to the x, or 10 to the x. Okay, so here we are going to be looking at exponential functions, but specifically one type, the natural exponential function. And that the natural exponential function uses a particular constant for the base. So it's not 2 to the x, it's not 3 to the x, it's not 4 to the x that we're going to be looking at here. What we will be looking at is e to the x. Okay, so the number e. So let's talk briefly about the number e. Okay, so this is E for Euler. Well, actually, maybe not for his name, but E as in Euler. Euler, Euler. So here, it comes from this formula here, 1 plus 1 over n to the n. That's an n. Let me write that more clearly. And what happens is we inspect this value here as n gets very, very large. And you can experiment this on your own time with a calculator. Just plug in, like start with plug in 1 and see what answer you get. And then plug in 5 and then 10 and then plug in 100 for n and then plug in 1,000 for n and then plug in 1,000,000 for n and then see what happens and see what kind of answer you're going to get. What happens is you would think that, oh, okay, if you keep plugging in bigger numbers, you're just the result will just keep increasing. So it does that at the beginning. So when you enter 1, 2, 5, 20, 40, 50, okay, yes, that's true. It does increase. But then you actually reach a certain point, up around 100, 1,000, and it just kind of tapers off, and it just kind of hovers around a particular value. And that value turns out to be 2.718. Okay, so right around there, that's what you end up getting. So whether you plug in 10,000, like when you plug in 1,000, you'll get like 2.716. And then you plug in 10,000 for n. When you plug in 10,000 for n, then you get 2.718. And then you plug in 100,000 and you get 2.7182, and then 1,000,000 and you still get 2.71828, so it starts to taper off right around 2.718. Okay, and that number that it tapers off at, that's what E is. Okay, so E is approximately equal to, it's an irrational number like pi, 2.71828, and it just goes on and on. Okay, but you do have this button on your calculator just like you have the pi button. Okay, so the natural exponential function, we know what exponential functions are, but the natural exponential function would be in this form. So an exponential function would be like 2 to the x, right? 3 to the x, 10 to the x. This is also an exponential function. The natural exponential function uses e for the base. Okay? And when we evaluate, we're going to go ahead and use the E button on our calculator. So make sure you can locate that. You'll need a scientific calculator. Okay, so, and make sure you try these along with me with your calculator because, again, just like the previous section, students will often miss this on a test because they punched it into their calculator incorrectly. So do this together with me. So let's go ahead and try these. Evaluate. And let's try e to the third power. So go ahead and see if you can punch this into your calculator. If you're using a handheld calculator and you're not using the one on your phone, depending on the calculator, you might actually have to enter the exponent first and then hit the E button. So you'll have to experiment with it and see if you get this 20.08554. Okay. So if you don't get that, see if you need to enter the exponent first. Okay. And then try this one. 2 times e to the negative 0.53. Okay. Punch that into your calculator and make sure you are getting 1.17721. Okay. And then try this one as well, e to the 4.8, and see if you are able to get 121.51042. Okay. And I quickly went over how E is obtained here, but I'm also including a really short video. It's very engaging about how they calculate E. So make sure you look for that YouTube video. It's titled "The Number E." Okay, on Canvas. Okay, so hopefully you were able to get those three uh, answers when you punched them into your calculator. All right, so let's take a look at graphing. So graphing is going to work the same way as graphing in the previous section. Okay, so same method. Okay, and because e is a number that's greater than 1, we know we're going to have exponential growth, right? We have an exponential decay if the number is between 0 and 1. Okay. All right, so let's go ahead and graph f of x, which equals e to the x. So again, here, if you take some values, if x is 0, we still get 1. If x is 1, we get 2.718. Okay. $2.718, and we have our exponential growth. Okay. Okay, if we have this, if we graph f of x, which equals e to the negative x, so this one's going to reflect the graph over the y-axis. Okay, so you could do that transformation, but again, like these to me, I feel are just as easy if we make a table for this actual function instead of using the parent function. So if I plug 0 in, e to the negative 0 is still going to be 1. If I plug in negative 1, then I get e to the first power, which is 2.718. And so we end up with this graph 0, 1, negative 1, 2.718. So we see it's being reflected over the y-axis. Okay. And go ahead and try this one. Just use your calculator to come up with your values if you need to. Go ahead and graph f of x, which equals 3 times e to the 0.5x. Okay, so just go ahead and make a table of values. Okay, I'm going to choose 0 for x, so e to the 0 is 1 times 3 is 3. 1, I get 4.95 on my calculator. -1, I get 1.82. Okay. So 0, 3, 1, 2, 3, 1, and almost 5, -1, and 1.82. Okay. So we end up getting this graph. Okay. All right, applications. So we'll take a look at some compound interest problems. Okay, so applications. Okay, so let's just recall when we had compound interest, we had this formula from the last section. And that was when it was being compounded like quarterly or monthly and times per year, right? And we looked at that one problem where, okay, same amount of money, same amount of time, but what happens when it's compounded annually, semi-annually, quarterly, monthly, and daily? And then we notice that, the more times that it's being compounded, the more money we were making, right? So now, well, here, let me write this one. So this was the one that you had before, 1 plus r over n to the nt. This is the one you had before. So this is when you are having it compounded n times per year. And so now what we have here, since we noticed that, oh wow, we really like having that interest being compounded. It's like, okay, and if you watch the video on the number e, like you said, it's like, oh well, what if we can have it compounded not just daily, but what if we could have it hourly, the interest being compounded hourly? And then what if we could have it compounded every second and then every nanosecond, right? So when you have it compounded that often, like instantaneously and continuously, then that's when E comes into play. So we have this continuously compounded interest. Okay, and that formula is this. Okay, so A is our final amount at the end of that time period. P is our initial amount, our principal. E is not a variable. Okay, so don't think that E is a variable. E is that number on your calculator, 2.718. Okay, so A is your amount after T years. So that's still the same. Amount after T years. That's your final amount. Okay. P is still your initial amount, your principal. R is still your interest rate. And T is still your time. Okay, so the only thing that's different here is that we no longer have n because it's not being compounded a certain number of times per year anymore. It's being compounded continuously. Okay. All right, so then now you would get a problem like this. Find the amount after 3 years if 1,000 is invested at an interest rate of our wonderful 12% per year, compounded continuously. Okay, so we saw last time when it was compounded daily, we made like $433 and change, right? Like 27 cents. Okay, so we should make a little bit more than that, right? I think it was 27 cents. Okay, so the key word here is this word right here, continuously. So make sure that you are aware of this word. As soon as you see that word continuously, then you know you're going to be using a, oops, you know you're going to be using A equals PERT. Okay, this word means you're going to be using this formula. Okay, all right, so let's find that amount. 1,000 is our principal amount. E is the 2.718 to the R 0.12 times 3. Okay, so if you punch this into your calculator, then you'll get roughly $1,433, and now we get 33 cents. So we do get more, not much more, but we do get more, okay, than when it was compounded daily, and which is what we expected. We expected that if the interest rate was happening more often, then we should be making more money, and we actually do. Okay. Okay. Let's see. Let's take a look at this one here. An infectious disease begins to spread in a small city of population 10,000. Okay. After 10 days, oops, not 10. After T days, the number of people who have succumbed to the virus is modeled by the function V of t equals 10,000 all over 5 plus 1,245 e to the negative 0.97 t. Okay, So it's modeled by this function here. Don't let it scare you. It's there's only one variable here, t. Okay? E is 2.718. Okay, so here's the question. How many infected people are there initially? So oftentimes people ask, oh, how many are infected after 10 years or whatever it is? But, hardly hardly ever do they ask, oh, well, how many people were infected initially? So how many infected people are there initially? And that means at time 0. Okay. And like I said, there's only one variable here, t. Okay, so all you have to do is evaluate this function for t equals 0. So then that would be 10,000 over 5 plus 1,245 e to the negative 0.97 times 0, right? And so this would be 10,000 over 1,250. And this would equal 8. So there were 8 people initially. Okay. And then find the number of infected people after 1 day, 2 days, and 5 days. Okay. 1 day, 2 days, and 5 days. So that's like saying you need to find v of 1, you have to find v of 2, and you need to find v of 5. Okay? All right, so if you want to try those 3 on your own and then come back and check your answer with mine, go ahead and hit the pause button. Okay, so it's 10,000 over 5 plus 1,245 e to the negative 0.97 times 1. And if you punch that into your calculator, so initially there were 8. After 1 day, now there's 21 people that are infected. And then over here, after 2 days, let's see how many people are infected. 10,000 over 5 plus 1,245 e to the negative 0.97 times 2. Okay, so initially there were 8 people infected, and then after 1 day, 21 people are infected, and after 2 days, this turns out to be 54, and then after 5 days, we get 1,245 e to the negative 0.97 times 5. And after 5 days, now it's at 678. So you can see how here, when they're talking about exponential growth, you can see how concerning this becomes, because again, and you can see by the graphs that in a short period of time, we go from a small number, 8, to something very high very quickly. Okay, so so this e number is the natural exponential function, because e is used in a lot of things that happen in nature. that happen naturally, like population growth, like the growth of a virus, like radioactive decay, all of those different things. All right, so that concludes 4.2. If you have any questions, make sure you text me or email me. And hopefully you're keeping up with the homework. I will see you next time.